welcome back. So this talk is based on some work in the last 2 or 3 years. It started with 2 or 3 papers with the UBC and ex-UBC group. And at the same time, there was a very nice work in Saclay by Gabriele and Eric Perlmutter, and we combined forces. And we have 1 paper out, but we have many more other papers to come, so I'll try to summarize this. So this is 1 hour talk, which is a little bit long, and it's also almost the end of the conference, so I'll try to kind of give an overview with some introduction, some long introduction, because most of you have not worked not just on this topic, but on sort of the topics that are relevant to it. So I'll try to, basically my goal is to, for you to sort of understand what I'm doing, maybe kind of sympathize and maybe also find that interesting. And then towards the end, there are some technical details and some formulas, and I'll try not to get too much into that. I certainly won't go over time. And lots of questions would be good. So I find this talking to different audiences requires changing this talk completely. So last time I gave it was a bunch of mathematicians. Here it's mostly high energy theorists, I'm assuming, not too many condensed matter people. So, you know, I hope I pitched it the right way. So I'll start with a summary, just while I still have your attention, of basically what I'm trying to do, and then a little bit later about, you know, how I'm proposing to do that. So the basic thing is that we're trying to generalize what's called chaos. So I have to tell you a little bit what I mean by that, and partially it's the title of the talk. It has to do with the notion of randomness. So this is very well developed for quantum mechanical systems, things that have time but don't have any spatial extent. Those are the simplest kind of system. They typically don't have any additional symmetries. Sometimes you even talk about time-dependent Hamiltonians, so they really have no even energy conservation. Very simple system. And this is very well understood there. And what happens is that you look at excited state, which is not what you normally look at as a high-energy physicist. So you're not focused on the vacuum and a few excitation above the vacuum, but you're really talking about very excited states, which are very dense. There's exponentially many of those states. And you try to characterize the statistics of those states. And the reason why you want to do that is that you discover that there's another notion of universality when you do that. There is universality more or less in a similar sense that you have in low energy physics, with many mechanical similarities. This is sometimes called RMT universality, which I really don't like, so will try to explain. In some sense, we're trying to generalize RMT, so I have to tell you what aspect of RMT we're trying to generalize. And the reason why we're interested in that as physicists is that these statistics, those properties of excited state, govern certain properties of physical processes, thermalization, any sort of long-time dynamics of, say, thermal states. So this is kind of the large context of what's sometimes called quantum chaos. So this is one context. The other context is we're interested in random matrix integrals for very many decades now, because they're dual to low-dimensional gravitational theory, and this has been kind of revived in the last few years in the context of dilaton gravity theories. So this is something that has some independent interest. And in particular, in two-dimensional gravity, in JT gravity, the gravitational theory is dual, literally dual to a matrix integral. And if you're interested in other aspects of low-dimensional gravity, you might want to learn lessons from that duality. One of the lessons, which I think is a little unfortunate, was this idea of ensemble average, that somehow in higher dimension as well, you have some sum over Hamiltonians, like you do in random matrix theory. I don't know if that will make sense. But this is an additional motivation to be interested in generalizing the idea of random matrices to higher dimension, or at least one higher dimension. as we'll do here. The other motivation, which I'm really not an expert on, but I urge anybody who is an expert on to maybe talk to me, is that random matrix theories are very much interesting objects geometrically. They encode some information about the moduli space of Riemann surfaces, KdV hierarchy, intersection number of moduli space, the loop equations. There's a whole bunch of very interesting math that I'm kind of very slowly learning. My background did not prepare me to sort of the more mathematical physics aspects of it, but I think all of this thing is also generalizable in some interesting directions. So there are three motivations here, and in some sense they're independent. So the idea is that you take all these three aspects, and sometimes they're kind of completely independent to each other, and you try to generalize all of them to higher dimension. And eventually the idea here is to talk about any sort of four-dimensional, say, quantum field theory. The questions normally are also interesting in that context. So any quantum field theory will have long-time dynamics, and it will have excited states, and the long-time dynamics will be probably related to some statistical properties of these excited states. But the problem with this is that the system is a lot more complicated. This is the reason, I think, that originally all this notion of statistics and chaos were investigated in quantum mechanics, because you have structure. Generally, you have a structure that has to be disentangled from randomness, because you have two things that compete with each other. You have, say, a specially extended system, so therefore the Hamiltonian is not the most general structure. You have some sort of sparseness in the Hamiltonian. Every site, every location on your spatial direction is only talking to its nearest neighbor, or in some local way. So you'll have a lot of zeros in your Hamiltonian. You cannot assume it's completely random, because this contradicts locality. So this is one way in which you can't really use the same tools that you did before. You have to incorporate this new structure in your idea of what is random. The other thing is that related to that is you have symmetries. And symmetries in the original quantum chaos, as I'll show, are kind of easy or straightforward to disentangle. You basically just go to a symmetry sector, some fixed charges, and then you're done. But here it's going to be a lot more complicated to do that mechanically, maybe also conceptually. So you have all kind of structure in higher dimensional theories that competes with the idea of randomness. So the first thing that we'll have to do is to discuss what sort of object could be random, and what objects are just determined by symmetries, and disentangle all those aspects very carefully. So, as I said, the program here is much more ambitious than just what I'm going to talk about, which is going to be just the simplest system that extends beyond quantum mechanics. This is two-dimensional conformal field theories. You might hope to say a lot of things, because you have a lot of symmetries, and you have a lot of example and experience with thinking about conformal field theories. And the idea is that you want to characterize the spectrum of two-dimensional conformal field theory. You have a spectrum of conformal dimensions. This is a series of erratic numbers. There's exponentially many of them, and you want to characterize them statistically. That's the idea. And the hope is that they also tell you something about the physics of conformal field theory in that regime, finite temperature and long time. Okay? And the main technical issue, as I said, there is the symmetries in conformal field theories, and the symmetries act much more in a much more complicated way than they do in quantum mechanics. You have constraints from symmetries that are known generally as bootstrap constraint, and those are complicated and much harder to disentangle than the normal symmetries of a quantum mechanical system. So this is kind of the quick summary. So hopefully that was kind of understandable, and then I will try to go over those points one by one. So the first part of this talk, I'm going to talk about the background of what we're trying to generalize. So as I already said, random matrix theory comes about in many different ways in quantum mechanics and in quantum gravity, and all of them are interesting, but they're kind of independent. So when I make a statement, I'll try to be very careful about, which one of the aspects of random matrix theory I'm trying to generalize. I'm going to discuss spectral properties of a quantum mechanical system. This is the thing that we'll be focusing on. There's very interesting work on other properties, but this is the thing that we're going to focus on. And in particular, just state a little bit why the issue of symmetries is very interesting, or it's an obstacle, depending how you look at it. In the second part, I'll talk about chaos in two-dimensional CFT, and this is kind of the technical part where I try to say what is the approach that we take in order to determine these statistical properties. And it turns out that there's some sort of bootstrappy way of doing the thing that we want to do, and this is based on two kind of hints that I call axioms, because none of them is kind of a rigorous property of conformal field theories that I know for sure, but these are the parts that we take as starting points. So the starting points are basically two, you have these two properties. One of them is that there is a certain limit of conformal field theories in which you expect them to reduce to quantum mechanics. The simplest way to think about it is some Kaluza-Klein limit in which you just compactify your theory on a circle and send the circle to be very large, and then you go to the zero mode sector. But there's kind of hints that there is generalization of that, which we call the near extremal limit. And there are some examples. Again, none of it is rigorous, but this is our hint. So in that limit, what we expect is that it's a quantum mechanical system, and you just get the properties of quantum mechanical system that you know. For example, the spectral properties of quantum mechanical system should emerge with whatever structure that we find should emerge in that limit. So in some sense, this is the boundary condition of your problem. And the second axiom is that you have certain symmetries. And most of the symmetries act in a way that's very easy to disentangle. I'm going to review that, but modular invariance is a little bit more complicated. But also interesting because the objects in conformal field theory are very interesting mathematical objects, the modular forms, and in some sense what we're seeking is generalization of RMT to include or to apply to modular forms. So I think this is interesting. So what we'll find, which is kind of a little bit surprising maybe, that self-consistently you impose these two things. There's a certain limit of your modular forms that encodes information about normal RMT, and the fact that they're modular form, this kind of determines uniquely some minimal object that obeys both the limit and the symmetry properties. And that's maybe a little bit surprising, but we find for all the example that we look at that there is sort of a uniqueness. It's not really a uniqueness, but there is some minimal ansatz that gives you a modular form that has the required limit. And for that, we need the modular invariant decomposition of partition functions. I'm going to review that. That's a very interesting subject. When I talk to mathematicians, most of the talk was about that, but I was just going to very quickly review what it is. I think it has very interesting properties, and it's very interesting that we use those properties very strongly. There's certain properties of this modular invariant decomposition of modular forms that shows up in quantum chaos. That's kind of the message from that. And I'm going to demonstrate, if I get to that, we have a general prescription, so we're not limited by what I'm going to discuss, but it's much easier to talk about the prescription for the spin zero sector of the CFT, just because, you know, the formula simplify, and it's very transparent what is the input and what is the output in this formulation. So I'm going to talk about that, spin zero. which get contribution from the Eisenstein series, and then I'll talk a little bit about what emerges from this analysis, which is this idea of gravity of max RMT. And I can just say right now that we build some minimal object, and that minimal object just comes out of the analysis, and it obeys all the symmetries and the other restrictions. And it turns out that whenever we can calculate this, and we can calculate a gravitational path integral for the same quantity, we find that the answer is identical for reasons that we don't understand. It didn't have to be the case because we just have an object which is minimal in some sense, in the sense that we haven't quantified very carefully yet. And that minimal object turns out to be gravity path integral on the nose. So this is what actually the other group called max RMT, this idea that somehow gravity is the theory that is closest as possible to a random system. And we don't have a very rigorous or very good understanding of that. And then I'm going to talk about examples. I suspect that I won't. If I'm successful and explain myself carefully, I won't get to that, but there's a few examples of how to apply this and what are the features of the result we get from this analysis. And yeah, there'll be a slide of future directions. Any questions? Okay, let's see. Okay, good. Okay, so let me just talk a little bit about RMT and quantum chaos. So the first time that you think about RMT, or the first time that you find RMT, is this idea of quantum chaos. So let me be a little bit more careful about precisely what's the relation. So as I said, there's this degree of universality. This universality doesn't really show up when you talk about a single quantum system, but it shows up when you do some sort of coarse graining and you talk about statistics. Okay? Now, physically, this is to be thought of as a regime, a universal regime, which is you work at finite temperature or at excited states, so you can do things microcanonically or canonically, and you look at very long time. Or in other words, you're looking for low frequencies, but those are frequencies that are Lorentzian. So this is different from the universality that you get at low temperature or low energy physics. So we're talking about high energies and long times. And we'll see that, well, we won't see, but I will tell you that there is an effective field theory of that regime. And this effective field theory is what you can call quantum chaos, or at least what I will call quantum chaos. It's the effective description of long-time physics at finite temperature. So this is physically well-defined. It's well-defined in quantum mechanics, but also in any other theory that you might be interested in. And this has some effective description, and that effective description is useful for certain type of questions.
Question.
Yes.
Is it clear how to relate that notion of chaos to the classical notion of chaos, of phase-space diverging?
So generally I would say, so this is something that there's very interesting articles of Michael Berry on that. So I would say the quantum chaos is independent of classical chaos. The limits of long time and h bar equals to 0 do not commute. So it's really nothing to do with classical chaos, the type of chaos that I'm discussing. And there's a sort of a physics today of Michael Berry from back in the day that explains it beautifully. Okay. So in low temperature physics, when you have phases and you want to classify phases, you usually have some sort of Landau classification. You classify things by symmetries and their realization. And this Landau paradigm not supposed to be true anymore, but then maybe it's making a comeback now with generalized symmetries. So this is sort of the type of thing that you should have in mind. The different kind of phases that you have are realized as maybe patterns of symmetry breaking. You can make that more precise, but I just want you to have a mental image. And the different phases has to do with statistics of excited states. Okay. And what I'll be interested mostly in what I call ergodic phase. I use the word ergodic to kind of separate that out from other words like chaos, which have an ambiguous meaning. For example, for many of us in the high energy community, chaos refers to Lyapunov behavior, but this is not that. We're talking about times that are much longer than Lyapunov regime. We're talking about very long time of the order of the Heisenberg time. And therefore I'm using a different term. This term is ergodicity, just to use a different word. So this characterized, for example, by eigenvalue repulsion. That will be the first thing that we'll discuss in an attempt to generalize. And in low temperature physics, many times you're interested in universal properties and you want to demonstrate them, let's say numerically or some analytic model or something. You have a canonical example where you go to and do calculation, some spin chain or something that exhibit those properties you're interested in. And one way of thinking about random matrix theory is exactly that. It's some nice example. You can do calculation very easily. And that nice example is in the ergodic phase. So as long as you're interested in universal properties, then may as well use that one. You can use another one if you know to solve that other one. Okay. So this is one aspect of physics that we will try to generalize to higher dimension. Just the idea that you have some statistical properties which govern the long time finite temperature physics. And from that point of view, whether we have a generalization of RMT to a higher dimension, maybe, you know, instead of integrating over matrices, you integrate over matrices and tensors or something, it's a little secondary. Maybe this canonical example that make life simpler exists in higher dimension, or maybe it doesn't exist, but this is secondary. The thing that you're interested in is those ergodic properties and how to express them in some language. But there's the other interest, which is what I would call literal RMT. It's a little bit misleading because you would think that I mean integration over matrices with some measure, but even that notion has been a little generalized in the literature. But what I mean is RMT, including everything in RMT, not necessarily the universal physics of RMT, but even non-universal physics of RMT, like short-time physics. Okay, so RMT, like any other system, has universal properties and non-universal properties. If you're interested in RMT for its own sake, then you're interested in all of them. So in some sense, it's a different type of interest that you have as opposed to the first one. And finally, so we have two types of ways in which RMT could be expressed. The other one is the gravitational aspect of things. So models of low-dimensional gravities are, some models of them are dual to literal RMTs. You take matrices, you integrate over them, you take some limit possibly, some double scaling limit, and you get a theory that has a dual or equivalent description in terms of some gravitational path integrals with some action. So this is interesting. So then you might think that if you uplift it one more dimension and you discuss some formulation of two-dimensional theories, then you might have some expectation or some hope that this will be related to three-dimensional gravity. If you're really ambitious, you might think about going above three dimension, but at least if you try to go one dimension up, then you might think that whatever you're doing will have some relation to three-dimensional gravity which is asymptotically ideal. Okay, so we have three motivations and three ways in which RMT kind of appears in physics, and in particular in gravity. And I want to kind of uplift all of them to one more dimension. Okay, and I will try to present results in a way that distinguish between them. I would say that our results, as they pertain to quantum chaos, are correct because they're sort of tautological. as we'll see. They just give something that's almost manifestly true. I'm sure if you work hard, you can find loopholes. For the other thing, if you think about RMT as an interesting object in its own right, or if you think about RMT as being dual to gravity, those generalizations are much more speculative. We'll see that indeed the result that we find have some sort of gravitational flavor. They seem to be related to gravity on ADS3, but we don't understand why this comes about. This is just maybe a phenomenological observation. Okay, questions? All right. Okay, so let me talk a little bit about, trying to zoom in and be a little bit more quantitative here. So, and again, I realize that many people in the audience don't have the background, so I'm trying to be a little bit more pedagogical, I guess. So the idea is as follows. So you have this two examples here. You have a long sequence, or as long as ChatGPT gave me, sequence of numbers. And the numbers are erratic, okay? And you want to characterize somehow some properties of these numbers. Now, if you kind of assume this number are random, this is actually means something very constraining. It means that these numbers characterize some sort of organized process that generates those numbers. Not all erratic numbers come from this process that you can identify. So randomness, in that sense, I'm trying to distinguish it from the notion of having an erratic sequence, because randomness is very strong structure. So for example, the sequence on the left, it's what's called a Poisson process. You have a fixed probability distribution, and you keep doing experiments, you keep drawing from that distribution, and you generate numbers that are erratic. But each one of the sequences doesn't seem to have structure, but the statistics have a very strong notion of structure. For example, one way to quantify that is to look at what's called the level spacing distribution. You look at the gaps between any adjacent numbers on the sequence, and you do a histogram, and you see that there is a certain shape that emerges in the limit where the sequences are very long. And you can see the shape here is such that, for example, there's very good chance for degeneracies. Two numbers fall on top of each other. But there's also, relative to the other sequence, there's also some higher chance for large gaps in that sequence. So this is the Poisson process. On the other hand, you can talk about eigenvalues of some large random matrix. This is another process that generates the sequence, and that has different statistical properties. So you can see that you have what's called eigenvalue repulsion. The probability of two eigenvalues being coincident, it goes to 0. Okay. And also you have much fewer gaps, large gaps in that, because the probability for large gaps goes to 0 much faster than the Poisson process. So they look different, and you can quantify that difference. And this level spacing distribution has a maximum, so this is maybe like a lattice. You have some preferred distance between adjacent eigenvalues, and you fluctuate a little bit around that. So from that point of view, what I want to do is, suppose I generate now a series of other what looks like erratic numbers. I hope it's a pseudo-random process, which is H and H bar for a two-dimensional CFT. So I have a two-dimensional CFT. I want this to characterize this statistically, so I need this sequence to be long. So either you take a CFT of a very large central charge, or maybe you take a CFT and you look at some large charge sector where you have large entropy. And you want to characterize these numbers somehow. Okay. So the first thing that you notice is, unlike the previous case where you try to have a sequence of numbers, now you have a sequence of pairs of numbers. And those pairs, both of the numbers are not the same. One of the numbers is not erratic at all. So the spin in the conformal field theory is an integer, and the sequence 0, 1, 2, 3 has no interesting statistical properties. But the energies, let's say for fixed spin, are a large sequence. If you plot it, it looks pretty erratic. So maybe the idea is that you talk about the energies as kind of pseudo-random numbers, but you have to fix the spin. So this is the first kind of appearance of this theme, that in order to even talk about randomness, you have to kind of disregard all the consequences of symmetries. So in a conformal field theory, you have a conserved energy, but you also have conserved momentum. So you have additional charge, and that charge is very simple. And if you allow to discuss all the charges simultaneously, you're not going to see any distinction between randomness or non-randomness. The structure could be completely washed out. Yes? Yes?
The uniform probability for H.
No, I'm trying to deduce what is the probability distribution for H. I don't know what it is.
Right, but there are a sequence of random numbers.
Yeah, so what I'm trying to say is that, you know, before you talk about that, you better fix the spin, and then talk about the sequence of H plus H bar for fixed spin.
No, my question is that if you talk about Liouville field theory, the distribution, it's actually on the Liouville momentum.
Yeah, but that's continuous, right? Or
H are discrete numbers then.
H?
Your H.
H, yes.
They are discrete numbers.
Yes, that's right. Yes.
Okay.
So this is a unitary CFT with a vacuum.
No, I mean, Liouville is also unitary.
Okay, that's true. Yes.
Okay, thank you.
Good. So this is an example where you take 5 random matrices that are very large, and you kind of talk about them collectively. You look at the eigenvalue distribution, and you see it looks like Poisson. So, you know, it turns out that, you know, getting rid of the effect of chaos is very, very easy. If you take even 2 matrices that are chaotic and put them together and disregard the symmetries, then you won't see chaos. So the lesson from this is that if you want to see anything that's possibly pseudo-random, you better fix the symmetries. Okay, so this is the idea. Let me see how I'm doing with time. Okay, not too bad. Good. Good. So as I said, I have 2 hints that I'm going to take to be my starting point. One of them is the near extreme limit. So let me give you some sort of evidence, such as it is, that there is a limit in which things reduce to quantum mechanics. So as I said, the usual Kaluza-Klein reduction is an example in which you go from 2-dimensional theory to 1-dimensional theory. But there is something called the near extreme limit. So for example, there is a paper that shows that every large CFT has a Schwarzschild sector, which is kind of characterize quantum mechanics. Also, you can do a gravitational path integral, and there you can see very explicitly that this is the case. So you can do a gravitational path integral that calculates eigenvalue repulsion in some wormhole amplitude with 2 tori and ADS3. And when you take that limit, you do indeed reduce to 1 lower dimension. So our axiom number 1 is going to be that any quantity in this RMT2, which we're trying to construct, this is the unknown structure that we're trying to deduce, should go to the corresponding known quantities in RMT when you take this particular limit. And we'll see this limit is mathematically something that's very significant. And we want to get to the signature of quantum chaos in each spin sector separately. So quantum mechanics has a single Hamiltonian, but now we have a larger structure that has infinitely many Hamiltonians, one in each spin sector. Okay, and we want in the necessary extrema limit get the quantum chaos properties not just in the single spin sector, but infinitely many of those. So the result is kind of very highly constrained. The fact that there is a function that does the job is a surprise. Okay. Okay. Questions? Okay, so the second thing that I'm going to take as a hint is modular invariance. So I think this should be kind of known to most of you, but let me just discuss a little bit properties of conformal field theory and in particular its spectrum. So we will be interested in the partition function of two-dimensional CFTs. This is the object that is going to include the information about the spectrum, the energy spectrum of CFT, and the spin the spin content and the energy content of a two-dimensional CFT. Therefore, the partition function on the torus is a function of two numbers, which is tau, could be packages tau and tau bar, two complex parameter. And you can write that as a sum of your density of state as a function of h and h bar. Those are the numbers that I discussed, times the Virasoro characters. So there's a certain transformation that's fairly straightforward between the partition function and the density of state as a function of conformal dimension. So the Virasoro characters will take care of the contribution of all the descendants. So one of the symmetries that we want to fix is the Virasoro symmetry, the fact that each primary will have infinitely many descendants. The spectrum of the descendant is completely known, there's nothing random about that, so we want to disregard that aspect, and that's very easy. You basically look at the spectrum of primaries instead of just the full spectrum. Okay. So this means that you get rid of this Dedekind eta function. And now the other interesting thing that is significant here, you see this q goes to the power of h minus c, c minus 1 over 24. This is what is sometimes called the gap. And you see that the qualitative feature of this character are different whether you're above the gap, h is bigger than this number, c minus 1 over 24, or you below the gap. Okay, and this is something that we just mechanically use in order to isolate the states above the gap. These are the states we'll be interested in. Good. And of course, what is complicated here, since we're only talking about the spectrum, then there is kind of only one constraint, which is this constraint of modular invariance. So as you do a modular transformation on this tau parameter and tau bar, then you get the same partition function. This is a very non-trivial constraint on this spectrum of primary operators. So it mixes all the momentum sector, and it tells you that the object that you're constructing is different than the one-dimensional object. So the one-dimensional object will be lifting up naively into a random matrix for each spin sector separately. This would be your kind of first naive guess, because you do have to fix the momentum. Once you fix the momentum and you fix the Virasoro symmetries, but getting rid of all the descendants, then you might expect that the spectrum of primaries in each spin sector will be described by a random matrix. But modular invariants tell you that it cannot be the case. Those matrices are correlated. They're correlated in some kind of interesting, intricate way that is just one example of this bootstrap constraint. And the fact that the bootstrap constraint acts so non-trivially is what makes this problem mathematically involved. Okay, questions? All right, good. Good, so I don't want to go through all the details of this slide, but let me just say what is the point of that slide. So as I said, there's going to be an effort here to find an object that has a chance of being pseudo-random, okay? So you need to get rid of a few things here in order to have a hope. So one of those things is, I said there is a spectrum here which could be either above or below a certain gap. And typically what happened in the CFT, below the gap you have very few states, the identity, maybe a few others. So this is not something you can do statistics with. It's just like finite number of numbers. So the idea is that it's only the high energy states that are could be distributed with some interesting statistics. So the first thing you want to do is to disregard the effect of the low-lying states, like the vacuum, okay? But when you also discuss modular invariance, you see that each one of the states will have implication also on the high energy spectrum. It will have kind of modular images. So what we have to do is we want to kind of subtract some fixed. So we have our partition function, and we want to subtract some fixed modular form from it that is the consequence of the Cardi spectrum, basically. Okay. And this is something that you also do in quantum chaos, actually, because what you're interested in primarily is fluctuations around the average density of state. The average density of state itself is not the signal you're looking for. Now, as I said before, there's different characteristic, mathematical characterization of the states below the gap and above the gap. And it turns out that this is very useful for us because the states below the gap are non-normalizable states, and the states above the gap are normalizable states. So disregarding the state below the gap is very simply expressed in this language. You just say, I am looking in the end, I'm looking into a normalizable part of your partition function. Okay. Yes.
Is this decomposition unique in some sense?
No.
Like, so given a partition function that blows up, we can project it in many ways on the non-normalizable?
You can do it also in quantum chaos. You have a bunch of numbers, and you want to subtract the smooth part of the density of state. You can define that smooth part in many ways.
But there it's a local process somehow, like you're talking about unfolding?
No, I'm talking about, I'm talking about, for example, unfolding. But even before unfolding, you have to define your smooth part. And that definition is ambiguous. You have, for example, a window that you can average over, and the size of that window is ambiguous.
Right, so there it's a local thing. Here you have some global issues.
Yes, I could imagine that you can come up with some funky, well, what we did is a Poincare sum. I'm sure that you can come up with other prescription that will be crazy. So, yeah. The prescription that we have seems to make sense. Right. So I will probably cover about half of my talk, which is okay. Okay, all right, it's all fine. So the summary of all of that is now when we talk about the mechanics of that, we define something that could be pseudo-random. It's something that already incorporates all the symmetries into it. It's modular invariant. We already divided out the Virasoro. All of this is taken care of, so it could be potentially something that could be characterized statistically. And we also characterize that part that we isolated, very nice from a mathematical point of view. We're just saying this is a normalizable function on the fundamental domain. So this is what's called a modular form, which does not diverge at what's called the cusp. Okay. So this is one characterization. We now kind of isolated the sort of mathematical essence of this object that we're trying to find. And also we have this near extremal limit. And this near extremal limit is a particular limit of this function where we know what it is because we believe random matrix theory in that limit. Okay, so these are two axioms. Okay, let me just, again, I don't have too much time, so I just want to give the gist of what, how we do things. So because this is a normalizable function on the fundamental domain, we can use mathematical tools that are very useful. We can write this normalizable function in a complete basis of such normalizable function. Okay, so the fundamental domain is kind of something that looks like this, sometimes called a keyhole, even though I can't really see it. But it's, you can think about that as some domain where you have a function that obeys certain boundary condition, and you're trying to characterize these functions. And those functions have a basis, and the basis consists of two parts. The first part is what's called the real analytic Eisenstein series, to distinguish it from the non-real analytic, the one that just analytic. And this is a kind of scattering state. This fundamental domain has a non-compact part, and you expect a continuous spectrum. Very interestingly, there's also cusp forms, so those are bound states. So this problem will have kind of mainly unexpectedly a spectrum of bound states, so it will have a discrete spectrum. And that spectrum is very interesting all by itself. I'm not going to say anything about this except for that statement. For example, it has some statistics. So those numbers that appears there, their eigenvalues and the Fourier coefficient have statistics that could be investigated just by itself, and they have very fascinating properties, and those properties are relevant for us. That's all I have time to say. So this is arithmetic chaos. Yes. So let me, I think, probably conclude by telling you what's the consequence of all of that. So the prescription for the zero spin sector is very simple mathematically. So we take the input from random matrix theory. This is what we are wanting to reproduce in a certain limit of this function. And then we're going to write this function in a complete basis of functions that are modular and are normalizable. So there's going to be a part that's the continuous spectrum and a part that's the discrete spectrum. Now, why I'm restricting to spin zero is that this decomposition becomes very simple. So one thing is that the cusp form are defined not to have a spin zero part. So all this story with its beautiful aspects just goes away when we talk about spin zero. And the other thing is the Eisenstein series, if you truncate it also to the spin zero part, is very, very simple. So you can see the spin zero part of the Eisenstein series as two phases, basically. The coefficients of the second part is very interesting. It includes the zeta function. It has many interesting properties. But you know, for our purposes now, it's just some known function. And we want to express in this basis what it means to take the near extremal limit, and this turned out to be this particular limit of this parameter alpha. So now instead of talking about the parameters tau, we're talking about the parameters alpha. This is a different basis, and it's the composition you impose a particular known function as the limit. So we're starting with this known function, and we say in the near extremal limit, out of each one of these Eisenstein series contribution, the first term dominates over the second term. So in the near extremal limit, we forget about the second term, and we just have this single phase. So what's going to happen is that our step one is to take the input from RMT and express it in our language, which is this alpha basis. And the only thing that's relevant in this limit is this phase. So what we let to do is an inverse Mellin transform of this known function. So we take a function from RMT, any function that appears there as a universal result in RMT, and we inverse Mellin transform it just to express it in our basis. Okay? So this is our first step. And even this step is kind of interesting. I won't be able to go over it, but if you just do that and you express the known amplitudes in Mellin space, it seems to kind of express the structure of RMT in a very interesting way. Somehow the genus expansion comes about because of the analytic structure of the result in Mellin space. So it's already kind of an interesting exercise to do that. But now we can say, okay, what we get as a Mellin transform of the RMT input, this is some minimal ansatz. What I do is instead of talking about the first term here, this phase, this y to the I alpha, I now write the same expression including everything. Basically, the second term is the sum of all the modular images of the first term. So the minimal thing I can do is basically take the result from RMT and sum over images. And that's kind of the minimal modular completion of the result. Now, it's minimal and not unique because you can always add something that vanishes in the near extremal limit, so the result is necessarily ambiguous. But this is a well-defined algorithm for us to do this two-step process. You take an inverse Mellin transform, and you take the result and you just plug it in this spectral decomposition, and you interpret that as something that tells you something about the spectrum in 2 dimensions. Good. And let me just say that when you do that, so again, there's a very large ambiguity in all this story, but when you do that, you for all the cases that we have done that, you get something that's identical to the gravity answer. There's no reason it should be because of this ambiguity, but it turns out to be the case. So for example, the first calculation that we did is you have the 2-boundary wormhole. This gives a certain result in one-dimensional boundary theory. This is the famous ramp. And you can use our result to uplift it. So this is just, again, at this point, is just a bunch of mechanical steps that you do. You do that and you get a result which coincides with the result of Kotler-Jensen, which is the calculation of the gravity path integral with 2 boundaries that are tori. So this is the corresponding quantity in 1 higher dimension. So somehow we reach the conclusion that gravity is this object that maybe in some sense is as random as possible. I should say we have...
Moshe?
Yes.
But isn't it the same assumption? You go to very large, very low temperatures, you look at the leading part and you symmetrize that under modular transformations on both sides. Like,
no, it's
why is it the same procedure almost by construction?
It's not the same procedure because they do it. We can talk about that later. What you just said would lead to something that is a Poincare sum, but yeah, we'll talk about that. It's not obvious. It's not obvious. Good. And I should say, because I won't go over the examples, that we have now new calculation. So for example, maybe I'll flash that quickly. We have a 3-boundary wormhole. So this is a wormhole with 3 tori in the boundary, and you can sort of go through the process that I'm discussing here. The 3-point function of the density of state is universal in RMT, it turns out, at least for certain class of density of states. And you go through this process, and this process is a little bit more difficult because there are divergences that we have to talk about precisely, but you get an answer, and that answer has not been calculated in gravity yet, but all indication that we have is that if you calculate that in gravity, we get the same answer. Okay. Calculation is different, and you have to worry about many issues like mapping class group and things like that, but eventually, I think when the dust settles, we have a very simplified heuristic calculation in the appendix of our paper, but I'm told that there's a calculation in progress, and all indications are that it substantiates this max RMT idea. And I should say that we also have the 4-point, the 5-point, we have very specific expressions in our paper that are waiting for the gravity people to calculate them. Yes.
Question?
Yes, I think, yeah.
Is there an honest calculation even in the two-boundary case? Because Kotler-Jensen have a very wishy-washy argument for some zero-mode factor in their thing. So would that not be the first thing to do, honestly, before you do the three-boundary one?
Yeah, I feel like I should let Christian and Jordan defend that. I think it's honest.
No, they admit it's not computed directly, I guess. So.
I think from the first paper in the gravity story, I thought they computed that. You say no? Okay.
Not really.
Okay. All right.
Another question was how do you have anything new to say about the negative spectral density of Maloney-Witten and so on?
No. That's very interesting. I think Eric and Gabriele had a paper on that, but I think there's more to be said about that. I should say generally, I think this machinery could be used for all kind of questions. We use it for this specific set of questions, but I think, for example, what you just said could be very interesting to look at from this point of view. But to my knowledge, no. Okay, so I promise not to run out of time, so I will just flash that. These are my future directions. There's more, and all of you are invited to discuss things with me, and I just leave it at that.
Perfect. We have 3 minutes for questions. So, more discussion.
Maybe it's a contrived question, but so with a student, we have a paper in which we analyze how correlation functions change. So, for example, you have a Hamiltonian with, let's say, universality, as you said, like level repulsion, or else you have an integrable Hamiltonian with Poisson statistics. Yeah. And we just play so to change the Hamiltonian, just the spectrum of the Hamiltonian. So you just can build another Hamiltonian. You start with your Hamiltonian. You mean
parametric statistics, something like that?
You just change the statistics without changing anything else. You can just change the spectrum, taking with another statistics.
Right.
And you prove that correlation functions are not altered at all, until, of course, very late times. What I wonder is whether the question of gravity being really chaotic in this sense, or I mean, it's physical or not, I could just change the spectrum. The leading disk results for correlation functions will all be the same. We have maximal chaos, we have black hole entropy, we have galaxies, we have everything, and it still would be a theory without.
But the calculation you get from gravity, what you would get in general is that in the universal regime, things will not change as you change that, but in the early time regimes, things will change. So, you know, so you have in quantum mechanics the ramp and plateau, but before that, you have all kind of features that depend on the specific system.
No, but those won't change. Those that, for example, the chaotic, the Lyapunov exponent, the thermalization, ergodicity, those won't change.
So you're talking about all kind of universal properties.
Everything that is correlation functions doesn't change.
All features of all correlation functions, that sounds very strong.
Well, yeah. Well, this is actually very in parallel with what you said about that Michael Berry said, that these two things are unrelated.
No, but I'm now not talking that limits where you talk a very long time. I'm talking about short time quantities. So these are non-universal properties. And those non-universal properties are not needed in gravity, it turns out. So if you change your spectrum a little bit, then, you know, at very late time, universality tells you get the same answer. But at early time, you get all kind of...
No, it's the contrary. It's the contrary. If you change, I mean, I'm changing the spectrum in a very like kind of. So I'm leaving the density of states unchanged, the coarse grain density of states, but just changing the statistics. So the density of states is what enters in the computation of correlation function at early times, and those won't be changed.
No, I
You
mean,
can see it numerically. Well, we can discuss later.
yeah,
I just
let's
wanted to-
discuss. I'm not really sure I understand exactly what you're, yeah.
Yeah, quick. Yeah. So in the beginning, you mentioned something like ensemble averaging for higher dimension.
Sorry?
You mentioned something ensemble averaging for
Yes, yes, yes.
higher dimension. But we know like higher dimension we have only single.
This is a
Like
charge.
what's the status? Like what do you comment like?
Well, I mean, this is a charge issue, but you know, I mean, for my philosophy, my religious belief is that in higher dimension, you cannot make sense out of ensemble averaging of Hamiltonians, because it doesn't seem like you have a family of Hamiltonian. But if you think about universal properties, self-averaging properties, you don't really need all this extra structure. But you know, this is a very charged question. Lots of people have different opinions, and you know, yeah. But just because I don't think you can make sense out of ensemble average in a higher dimension, you have to do something that does make sense. And the thing that always makes sense is you look at universal properties and you look at self-averaging quantities, and those seem to be always well-defined in any context.
Great. So we'll relegate further discussion to the coffee break, and let's thank Moshe again.
Thank you.
Okay, now let Francisco set up.